Okay, let's try another example for the T distribution. We have a company has a set goal of developing a battery that lasts over 5 hours or 300 minutes in continuous use. In the first test of 12 batteries, they measured the following lifespan in minutes. Here's the data set. We want to find a 90% confidence interval for the mean lifespan of this type of battery. Well, to start off with, the first thing I'm going to do is I'm going to name the test. I'm going to have a T interval. Let me make a thinner pen here. It's going to be a T interval. And I'm going to throw these numbers into my calculator so that I can get the rest of my numbers. And you can see I've already put it into L1. And so I'm going to go statistics, calculate one variable statistics. Everyone counts as 1. And here are my numbers. X bar is 306.25. My standard deviation is 29.3. My N is 12, so my degrees of freedom are 11. And just to double check, 3675, I did no typos. And so the other thing I'm going to need is T star for 11 degrees. And so if I go to second distributions, I'm going to go inverse normal, or inverse T, sorry. My area, I want a 90% confidence interval. So my area is going to be 0.05. Degrees of freedom was 11. So my T star is going to be 1.796. Here are all the numbers that I want. And so my confidence interval is X bar plus or minus T star or 11 degrees of S over root N. Plug in these values in, 306.95 plus or minus 1.796 times 29.3 over the square root of 12. And when I do that calculation, I am going to do stat to tests. I know it, to tests. I know it's number 8 from my memory. I'm going to go to the data, L1, frequency 1. My confidence level is going to be, and I like to use my calculator for this because it keeps all the decimal places for all these values, and so it will be accurate to 3 significant figures. And so my confidence interval is as such: 291.05 to 321.45. And so my conclusion is we are 90% confident that the true battery life mean is in between 291 and 321 to 3 significant figures. Okay, so there's the confidence interval. We named it, we did the numbers, showed the calculations, and concluded in context. A part done. Is there evidence the company has met its goal? Explain. Well, my confidence interval is 291 to 321. My goal, they wanted to last over 300 minutes. And so the answer is yes. And so B, the answer is yes. Let me try that again. As 300 minutes is in the interval. So we believe that they have met their goal. Now, we are only 90% confident that the true value of the mean is in here. And so if we would repeat this experiment with more batteries, numerous times, only 90% of those confidence intervals would actually capture the true mean of the population. We don't know if this is part of the 90% or part of the 10% that does not capture the mean. And so we never know if it's there or not. We just have faith in our statistics or our calculations. So if it is wrong, what type of error may have occurred and what would the consequences be? Well, if it is wrong, right? If it is wrong, then we have said it is true of over 300 minutes when it is not over 300. Well, it could be lower. So if lower, then what? Well, if it's lower, then my battery lives are going to be like 290 or 270. And I'm advertising that there's 300 minutes, but this is the truth. Well, the consequences are I could get sued for lying, right? My reputation as a battery manufacturer, everyone's going, oh, these batteries they say they're supposed to be 300, but they're definitely less than that. So we could also lose our reputation. If it is higher, it's possible that it's way more than 300. If it's higher, there's consequences to that as well, being that we are advertising it does over 300, but really we could have more advertising saying, oh, it lasts for 320 minutes or whatever we think the true mean is, which will be more bang for the buck, so to speak, in advertising. Also, maybe you could charge more for more minutes of battery life. So there's consequences either way. We hope we get it right in statistics, but we never actually know. So those are the consequences. And then finally, we wish to conduct another trial. How many batteries must we test to be 98% sure of estimating the mean lifespan to 15 minutes? Well, if I'm going to do that calculation, that means I am looking for n. I want my lifespan to be 15 minutes. So within 15 minutes, that means when I have my 300, I go plus or minus 15. This 15 is what we call our margin of error. And I know the margin of error is going to be T star times S over root n. And that's going to be 15. And so my S is easy. That's 229.3. My root n is what I'm looking for, but my T star is dependent upon n to get my degrees of freedom. So we're in a bit of a dilemma. And so what we do is we just choose one. And we've been using 11, so we choose 11. And this is not the end of it, though. And so I know it's 1.796 times the standard deviation is equal to 15. If I rearrange that, I'm going to flip the fraction, multiply, and so on. So I get the square root of n is equal to 1796 times 229.3 over 15, and I'm going to take this and square it. And when I do this calculation, I end up with 28.2. I could do it with my calculator, or you can just trust my word for it. So now I'm saying n is 28.2. Well, I don't know this for sure because this degrees of freedom was estimated. So what we do again is we do the same calculation a second time, except now we used our 28. Well, this n is 29, we round up. So degrees of freedom is 28. And we're going to do the same calculation, but with this particular t star. And if we rearrange this formula, let's just do it now. So I know that t star times s over the margin of error 15 is equal to root n, and so I square both sides. And so I have t star times 29.3 over 15 squared is going to be my n. Finding my t star 28, go to my distributions. Number 4, I know my area. Well, I'm looking to be 98% confident, which is 0.01. My degrees of freedom are 28. And that gets me 2.467. If I take that times 29.3 divided by 15, square it, and I get n is equal to 23.2. So I round it up to 24. So n is 24. And so if we would use 20, because this is an estimate again based upon an estimate, if we would use 24 again, what you'll see is that it actually comes back being 24 again. And so you really only have to do this procedure twice, and that should be fine. I did realize I did make a mistake. This value here, I should not have used t star, the 11 value from here, because my confidence interval was for 90%. I should have changed this value if I would have done it for inverse t. Number 4, I had to use 0.01, and this would be 11. And so this value would have been different, which would have affected later on. But the premise is solid, and it should work out okay for you.